Welcome to Week 7, Physical Computing. This week, we're going to talk about the shift register. The shift register is an IC component that makes it possible to control 8 outputs with just a couple of pins on your Arduino. And this is useful because you can greatly expand the output capacity of the Arduino. And as well, you can use it to control multiple chains of components, such as a wall of LEDs, which is something shift registers are really commonly used for. Shift registers do this in a really interesting way. They do it by having 8 bits of data that get fed into this IC and reading the 1 or the 0 as high or low, on or off. And if you're working with something like a wall of LEDs, this becomes a really obvious way to flip different pixels on and off in the display. Everything in computing can be distilled to binary, and this is a moment where the binary becomes really powerful. Each of these states is represented by either a 0 or a 1, either on or off. So in the case of the LED, a row of 8 zeros would indicate all the LEDs to be off, or a voltage of 0 volts. If, for example, we shift 1 bit in, we could turn the first LED on in the chain if we apply them that way, configured with our pins, obviously. You can wire your display however you want. But this process of shifting a bit into this 8-bit number is called bit shifting, and it uses the left shift operator in this case, meaning that we're going to come from the left side of the binary number, and we're going to move in a new element and shift the farthest left element out. So you can think of this as rolling bits in and rolling bits out. In this case, if you shift the very last bit, the bit in the, if you start counting at 1 being at the logical right to left, the 8th bit there would be the one that gets shifted in. This is a logical shift. You can go either right or left, so you can come in from the front of the 8-bit number or the back. And the shift register is essentially a left shift in hardware form. If you look at the truth table below, you'll see that in this case, if you look at the original starting set of numbers, which would be 0, 0, 0, 0, 0, 1, 0, 1. If you shift a 0 in on the left, what ends up happening is that 0 goes in, pops in on the left, the 1 moves over a slot, the 0 moves over a slot, the 1 moves over a slot. And now you're, instead of having 5 zeros on the left there, you now have 4. And I think that should be fairly obvious. Take a second and look at the bit shifted in and how the bit shifted out correspond. So the pin out of a shift register, it looks a lot like the IC we worked with last week. Again, the pin in the bottom left-hand corner is ground. The pin in the upper right-hand corner is power. There's going to be the little dip to indicate, which side is up, which side is down. All IC packages, as I mentioned last week, are quite similar. If you look at the pin out here, Q0 through Q7 and pin 15 are your output pins. These are the ones you're going to hook your LEDs up to. Q7 or pin 9 is the bit that gets rolled or shifted out, and pin 14 is the bit that gets rolled in. There is a master reclear, so if you want to empty your whole shift register, if you pull this to low, the whole register will get cleaned. And if it's, it has to be enabled to high to actually be enabled. It has to be pulled to high to be able to enable the shift register. If you look at the SHCP pin 11, this is the shift register clock pin. Clock pins are really important. When this pin is pulled high, it will shift the register. That means it'll take all the bits and whoosh. This pin will alternate between high and low. In our analogy, it's like the bell that indicates that a change will occur. The storage register clock pin needs to be pulled to high to have the pattern of the bits be pulled out by the register. This will be pulled high after the SHCP pin 12, when it goes low, after the sorry, my slides, my reading. My bad. So this pin needs to be pulled to high to have the pattern of the bits be pulled out by the register. This will be pulled high after the clock pin above has gone low. This will alternate between high and low as well. And the pin could be analogous to the display trigger. You could have multiple shifts, but only one display in the ending pattern. I hope that makes sense. You'll see it in the SparkFun video. It's much easier to see the way that the registers work with the clock pins when you actually just plug this thing in, and it makes a lot more sense. And then obviously the output enable pin. You can do this kind of thing where this pin enables the output when it's tied to ground, and it disables output when it's tied to high. Note how the circuit has pin 13 tied to ground. So I have a circuit on Tinkercad, you'll see later. So I hope that this is useful. You're going to need to care most about these 3 pins for the Arduino. The DS, the bit to be shifted in, obviously. The clock that controls when the output gets displayed, and the clock that controls when the shifting occurs. These are the 2 pins that, you really have to flip in and off. And then your display pin is going to depend on whatever value, a 0 or 1, you're putting into the register. When the signal on the SHCP pin goes high, all the values get shifted, and a new value from the digital pin gets shifted in. When you want the pattern that has been created to be output, you must also change the STCP pin to high. This updates the output. So shift in, show. You can think of them like that. This is the video that is in today's lecture. If you haven't watched it yet, I really encourage you to watch it, because talking about all these pins is a little bit confusing, but if you'll go look them up and see them work, it's pretty dead obvious. There is a bit of code attached to this week's class. You can now go find this on Moodle if you want to take a look at the code breakdown. It will show you exactly how to do this in code in Arduino, and we'll review that in a second later. Let's take a quick second now and review binary. There are only 10 types of people in the world, those who understand binary and those who do not. This is essentially saying there are 2 types of people in the world. And the reason for that is the binary number 10 is equivalent to the regular number, or the natural number 2. I have included a binary truth table here for those of you who've never seen one before. The first position represents a 1. I feel like I've shown this to you all before, but the first position represents a 1. The next position represents a 2. And these go up in powers of 2. So 1, 2, 4, 8, 16, 32, 64, and 128. And each one of those slots being on or off represents a value. And then all the values that are flipped on, you just add together to get the value that is the final output number. There are 1,000 videos on how to count in binary on the internet. And it's worth checking them out if you don't understand this, but it's pretty straightforward. You also, when you're working with shift registers, sometimes you'll run across the logical binary operators and or an XOR. And will output a 0. It'll compare 2 8-bit numbers together, and it'll output a 0 if both values contain a 0 in that slot. So in this position here, as you can see, 0, 0, output 0. 0, 0, output 0. 1, 1, outputs 1. So it compares to make sure those values are matching. And it outputs what the matching number is. The OR will output a 1 if either are 1. So in this case, you'll see 0, 0 is going to give you 0 all the way through here. And 1, 1 will give you 1. But also, you'll see that 0, 1 will give you 1. 0, 1, 1. 1, 0, 1, and 0, 1 will give you 1. So that's OR. And XOR is a number that is a strict OR operator. So it will output a 1 if, that's my bad. It will output a 1 if either of the numbers is a 1. But if both numbers are a 1, you'll get a 0. So it's a little bit subtle. So if you look at this number here, 0, 0 gives you a 0, 1, 1 gives you a 0, 0, 0 gives you a 0, but 0, 1 gives you a 1. So this looks to see if they're not matching, essentially. So you can chain shift registers together. You just put the pins one on the other. So you tie your your clocks and stuff. And it's a nice way to build these into really huge long displays. Eventually you'll run out of voltage. Matt and I can attest to this. We've fried many a thing this way. And there's an example of this on this website, which I put a link to, but is really riddled with ads these days, which makes me sad because it used to be a really good resource. But you can go there and see a video of it. You can wire this up in Tinkercad yourself, and I encourage you to give it a try yourself later on. And at this point in the class, I'm going to flip over to this circuit. So it turns out that these different numbers can also be used to control a 7-bit display. So instead of having 7 LEDs, you can use it to drive a 7-bit display. Obviously, this has uses in many ways. I do not know why this IC thinks it's lighting on fire, but Tinkercad, ask no questions. So I looked at this code. I found it on Tinkercad because this is just a basic Arduino sketch. I think it's even in most of the Arduino books. But here you'll see this is the only bit that's doing the magic. Each one of these numbers in Arduino, if you include a B before an 8-bit strain, it indicates it's a binary. Do not leave this off. It will kind of work, but not always. You have to have the B there. So in this case, what it's doing is it's getting the bits from the shift register, and depending on what those bits are, it's returning a number to be output on the display. So that's pretty much how this works. These are hexadecimal values. For a breakdown of how to translate binary into hexadecimal, it's a pretty easy process. Let's see if I can find a nice truth table here to show you. I mean, this is, obviously, if you just want to convert it this way. But the way it works, if memory serves, is you get up to 1, 2, 3, 4. I think you get to, 16, and then it goes to A. Hold on. I need to pull this up because I haven't looked at it in a hot second. But just click on images. It'll be really obvious. There we go. Yeah, so it compares 4 bits at a time. And those 4 bits, they go obviously 1. It's still 1, 2, 4, and 8, right? So once you hit, this will output up to the number 15. Once you hit 16, the number goes to a alphabetical number. So it goes like A, B, C, D, E, F. Aha, here's the table I was looking for. So it goes 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. I was right. It does go to 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, B, C, D, E, F. And those are 10, 11, 12, 13, 14, 15, 16. And then you just add all those values together to get the hexadecimal value. So if you look at it here, you can see that what's happening is this one is going to output a 3, this one's going to output a B, this one's going to output a 2, this one's going to output a 9, and then you just 3B, 2, 9. It's that simple. Cool. I will be honest with you. This is one of those things that I have in my Maker notebook that I refer to all the time. It's a really nice thing to keep a notebook of conversions and tables and symbols. I have one. I got it from Make Magazine. It's blue. I love it. You'll see them on the internet from time to time. They look like this. And in the back is a ton of useful tables and datas, and hex conversion is one of the tables in the back of this fantastic wee book. And I really love having an engineering notebook in general because it'll just help you keep track of stuff. So, these are some of the pages in the Maker notebook, and everybody forgets like these basic things all the time. Like, oh, what does that resistor color mean again? And there's a color table. Oh, what is this? What is that? And really simple little things like that are all in the Maker notebook. I love this thing. But just keeping a notebook in general of your engineering ideas is an incredibly good idea. And I would encourage everybody in this class to do it. So let's come over here and look at this again because it's just running. So we haven't looked at any basic Arduino code. So it might be worthwhile to take a second now and just look at the code from this week's class. So I'm going to come over and open up Arduino. And go. The code will be in Moodle. because there's been some structural changes to the class, obviously, since the COVID-19 crisis, but it should be really obvious to find on Moodle. It'll be in a folder called This Week's Code. In this case, I'm going to have to grab it from where it lives on my system, which will be obviously a different location for me than you. Okay, cool. Awesome. Boop. So class code, this is going to be it's already on the GitHub for this week, but okay. So let's pop this open. Okay. So this is the basic code for how to control a shift register. Here you'll see that I'm defining the data as pin 2. This is on the Arduino. I've just connected that data pin, that DS pin, to D2. I've connected the clock pin, the one that shifts the bits in, to 3. The latch, which will display everything, is on 4. And you'll see that I have all of this kind of just set up to be the data, the clock, and the latch. I have it all locked up here. So if you come over here really quick and you look at this IC and you just Google 74 HC595 shift register pin out, and we know the magic word, data sheet. You'll get a data sheet of the shift register. Let's make sure this is the right package. Yeah, we have this package, right? So we don't have the itty bitty IC package. But here you'll see, if you get confused, it's also in the slides. You can go look at it there. But you'll see that these 2 pins and this pin, so this is your clock. And if you come over here and look at it in Tinkercad, floop, and let's get this up over here and look at the pinout, or we can do it from the slide deck. Either works. So, you can just take a quick look. I'll close the code here. And, oh my. Okay. Stay. Okay. And here you'll see quite clearly that the pins that we have going to the Arduino are here. This one is the chained one. Which one is that one going to, out of curiosity? That's a ground connection. We talked about that earlier. And then and here and here. So those are the ones that are connected to Arduino, and these 3 pins are what are letting you control the shift register. So if you look at this pin, you'll see, is this the right package? Look at this. 1, 2, 1, 2. Count the legs. 3, 1, 2, 3. I feel like this shift register 85S. I feel like this might be a slightly different package. No, this would be okay. So then if we look at this, we'll see that this is connected to the clock pin. The next one up is connected to the RC. Sorry, I'm not very good at switching numbers upside down like this. 1, 2, 3, 4. So this is pin 12, 13, 14. No, sorry. 16, 15, 14, 13. Yeah, okay, so this is 13. And 15, 14. My dyslexia is fighting us here for a quick second. But you can just match these pins over to the side if you need to. You can rotate this, take a picture and rotate it. I recommend it if you're as dyslexic as I am. But here you'll see that the pins are clearly defined. And I would recommend, actually, instead of looking at the data sheet, it'd probably be easier to look at my slides, because I think that graph is actually a little bit clearer. Yeah, because I went through when I made these slides and defined everything. So here you'll see that the pin 11 and pin 12 are the SH and ST clock pins at the clock and the latch. And here you'll see that 14 is the data pin, which you can quite clearly see is connected here. I may have had I had the SN version of this package, which might have been slightly different here. Sometimes some of the packages will change based on the prefixing numbers. This looks like it's missing some of the things I was showing you. So if I look over here for a quick second, it's much more obvious. The data pin, right? This is the one that is the bit that's to be shifted in. Here you have the one that's tying it to ground, and we talked about that a second ago. Then this one is the STCP, and this one is the SHCP. And if you are curious what those mean, again, you can just come down here into the slides and check it out. And the pins that you care about are clearly defined on the slide deck here. So the clock is the one that controls when the output gets displayed, and the SHCP is the clock that controls when the shifting occurs. These pins are related as follows down here. So obviously you can see that this is hooked up here. So that's pretty obvious. You can check that out later. And I think that's about it. We're going to make a couple of these in class, so don't have a panic. Try and make one with just simple LEDs, maybe not as complicated as what this is. And if you want, I mean, I've just been Googling Tinkercad because it seems like they have a pretty endless display. So if you just go Tinkercad shift register LEDs, you will find one. So here's a, I think this is a really super, here's an obvious one. And there's the good thing about Tinkercad is most of the basic circuits have already been kind of laid out for you, and you can just look at them. So let's see, does this one work? All these wires are green. Whoever made this. But yeah, obviously this is a, one you could look at, and here you'll see that as they move through the loop, they're going to be shifting in a new bit. So do you see how they're shifting that bit down each time? Boom, 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 and shifting in another one. So if I look here, here's exactly that. So boo, 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 update. So here we go. So they're going through each one and they're setting it here. And so this is setting the bits and this is clearing the bits. So it's updating the register and shifting the bits. So that should be pretty obvious. Take a look at it. Let me know if you have any questions. And here you'll see that they're setting up the pins. So 11 is set up as the latch, 9 is the clock, 12 is the data pin. So the latch pin is the STCP pin, and then the SHC pin is the clock pin, and obviously the data pin. So just take a quick look at that, type this code, try and build the circuit. It'll make more sense. All right, that's it until we chat later. Let me know if you have any questions on the Slack. All right, take care. Bye, folks.